Hello, and welcome to our virtual presentation on our research titled ALLNet, a hybrid convolutional neural network to improve diagnosis of acute lymphocytic leukemia, also known as ALL in white blood cells. My name is Rishia Tavla, and the name of my co-author is Sai Madapali. First, we will give an introduction to acute lymphocytic leukemia, the different methods for diagnosing it, and the motivation behind creating ALLNet. Next, we will go over the different methods used in our research, including the data pre-processing, the model creation, the model training, and the model evaluation. The results of the research will then be reported. Finally, we will present our conclusions from our research and discuss the significance and applications of this research, as well as the methods to improve on ALLNet's current performance in future research. Leukemias are a subset of cancer that stem from the excessive proliferation of would-be blood cells, usually white blood cells. Acute lymphocytic leukemia, or ALL, is a type of leukemia that is acute or fast-growing. This is why it proves to be fatal even after only a few months, which makes quick and accurate diagnosis imperative. Additionally, ALL is initiated in lymphoid cells instead of myeloid cells, like some other forms of leukemia. ALL often starts in the bone marrow, where new blood cells are formulated but can spread throughout the body, even affecting the liver and central nervous system. Symptoms of ALL can include weight loss, a loss of one's appetite, recurring infections, pale skin, and more. Children 5 years old and younger are at the greatest risk of contracting ALL, as ALL is the most common type of cancer in children. This further highlights how imperative it is that ALL gets the attention it deserves in our fight against pediatric cancers. There are numerous different ways that a person can be tested for ALL. Since ALL begins in the bone marrow, doctors have multiple different tests and methods for identifying ALL in an individual's bone marrow, such as bone marrow biopsy and bone marrow aspiration. Both of these tests may result in the patient briefly feeling pain. As previously mentioned, the quality and level of healthy blood cell production in the body can also be affected by ALL, and so blood tests are another way to test for ALL. A doctor may also choose to administer a bone marrow test. Additionally, there are also a variety of imaging methods that doctors can use, such as X-rays, MRI scans, CT scans, and ultrasound. Imaging tests have an advantage over other types of tests due to their lack of radiation and their ease of administration. Due to a large number of ALL cases a year and its fast rate of progression throughout the body, a simple method to be able to test for and identify ALL as quickly as possible is essential to fighting it. This study aims to create ALLNet, an automated method for identifying if a given image of a cell is an ALL cell, so that once the images of a patient's blood cells are acquired, a doctor can briskly obtain a diagnosis. For this study, the machine learning models were trained and evaluated using data from the ALL challenge dataset of ISBI 2019. Each image was labeled by an expert based on their domain knowledge. The dataset includes data from 118 participants and 118 studies and includes a total of 10,691 images in the training set, with 7,272 of those images being of an ALL cell and 3,419 of those images being of a healthy cell. Each image is stored as a 450 by 450 by 3 array. Each label is either 0 or 1, with a label of 0 denoting that it is a healthy cell and a label of 1 denoting that it is an ALL cell. For the dataset, images from the original dataset's training set were taken and split into a training, cross-validation, and test set. They were split into a training set using 60% of the images, which is 6,414 images, a cross-validation set using 20% of the images, which is 2,138 images, and a test set using 20% of the images, which is 2,139 images. The images were then standardized using the mean and standard deviation of the images in the training set, which results in the data in the training set having a mean of 0 and a unit standard deviation. Finally, the images are resized to 250 by 250 by 3 arrays. VGG16 is a CNN architecture that achieved a top 1 accuracy of 0.713 and a top 5 accuracy of 0.901 on the ImageNet database. It is a relatively simple architecture and includes a series of 3 by 3 convolutions and max pooling layers. The VGG model used was built on a VGG16 model pre-trained on the ImageNet database. ResNet 50 is a CNN architecture that achieves a 0.749 top 1 accuracy and a 0.921 top 5 accuracy on the ImageNet database. It utilizes a series of residual blocks in which activations from previous layers are added to the activations of future layers. This helps prevent vanishing gradients, in which gradients get extremely close to zero towards the earlier layers of the network, which allows for deeper networks to be trained without losing performance. The ResNet model used was built on a ResNet 50 model pre-trained on the ImageNet database. Inception v3 is a CNN architecture that achieved 0.779 top 1 accuracy and 0.937 top 5 accuracy on the ImageNet database. The Inception v3 model applies multiple convolutional layers with different sized kernels and then concatenates them together. This lets the network try multiple different filter sizes rather than the programmer having to handpick them. The Inception model used was built on an Inception v3 model pre-trained on the ImageNet database. ALLNet is a hybrid CNN that combines Inception v3, VGG16, and ResNet 50 models that have been pre-trained on the ImageNet database. All of these model architectures are extremely powerful on their own, especially since they've already been pre-trained on the ImageNet database. However, this task is arduous because the ALL cells look almost identical to the healthy cells, and it is even more difficult in this case due to the relatively small number of images available to train the models on as a result of limitations on memory. To make a model with the ability to understand the subtle differences between the ALL cells and the healthy cells, a hybrid model that combines the strengths of each model is proposed so that the hybrid model will be able to gain a broader understanding of the data and the differences between the ALL cells and the healthy cells. The models, after being created, were then trained on the training set with 40 epochs and a batch size of 32. The images were loaded using an image generator which stores the file names and labels and loads the images for a single batch during training. When the image generator loads the images in, it also performs the needed data pre-processing steps. The models were trained to minimize their binary cross-entropy loss on the training set using the Atom optimizer with a learning rate of 0.001. The models were all trained using checkpoints, which saved the model that had the lowest cross-validation loss after each epoch. The models were all evaluated on the cross-validation set using the following metrics: accuracy, sensitivity, specificity, AUC score, and F1 score. These metrics were computed using the number of true positive, true negative, false positive, and false negative examples. Sensitivity and specificity were used to determine if the model had any bias towards positive or negative examples. AUC score was used as a metric of how likely the model is to predict a higher probability for a positive example than a negative one. The model should ideally output a probability close to 100% for a positive example and a probability close to 0% for a negative example. The F1 score was used to determine if the model had both high sensitivity and high specificity. After the models were evaluated on the cross-validation set, the best model was then determined using the previously mentioned metrics. This model was then evaluated on the test set using those same metrics to determine its performance on new data. As shown in Table 3, the proposed model ALLNet generally outperformed all of the other models in every metric. The only metric that it did not have the highest performance in was sensitivity, as it had a sensitivity of 95.5% and the Inception model had a sensitivity of 100%. However, the Inception model also had a specificity of 0%, which implies that the Inception model always guessed that a cell had ALL. Since the Inception model would never correctly diagnose a healthy cell, it is the worst classifier of the two. ALLNet would then be the best classifier out of all of the models tested. As shown in Table 4, ALLNet achieved a similar performance on the test set as it did on the cross-validation set. The model's accuracy only decreased from 92.7% to 92.1%. The model's specificity only decreased from 85.9% to 82.8%. The model's AUC score only decreased from 0.966 to 0.960, and the model's F1 score only decreased from 0.948 to 0.943. Additionally, the model's sensitivity increased from 95.5% to 96.5%. This suggests that the model did not suffer from overfitting on the cross-validation set, as otherwise the model would have performed far worse on the test set than it did on the cross-validation set. Through this study, we have developed a hybrid convolutional neural network model which can be used as an automated method for diagnosing ALL with imaging that is more efficient and faster than other common methods for ALL diagnosis. The high accuracy suggests that this methodology could be used for ALL classification in hospitals. Additionally, ALL was able to outperform other common CNN models that have achieved success on the ImageNet database, showing that the methodology could improve the accuracy of automated image-based ALL diagnosis. This also suggests that ALLNet and other hybrid CNN architectures could have applications to other medical imaging problems. In order to improve on ALLNet's current results, methods that future research could use are increasing the size of the dataset through data augmentation, training the model on more epochs, tuning the number of trainable layers, and using models pre-trained on different datasets. The most promising method for improvement is increasing dataset size, as the model was trained on a relatively small training set of 6,414 images. If the dataset size could be increased, it is possible for the model to achieve better results. Since it may take a large amount of time and resources to gather enough images to yield significant improvement, data augmentation is recommended, as it is a relatively quick and easy method for increasing dataset size that would not require gathering more images.